The second speaker is going to be Karen then, so maybe you have this already in mind. I will send you a short reminder 15 minutes into your slot. Okay? So I'll mute myself and give the floor to you.
Okay, thank you for the opportunity. And this is a joint work with Wenzheng Gao, who's also from Nankai University in Tianjin, China. So we're looking at the welfare effects of providing rank information to improve performance in the lab. Oh, sorry. Okay. So to motivate the study, I would like to put into the context of a growing interest from economists to measure the welfare effect of this nudging style policies. So the nudging style policies often require very small implementation cost on the part of the employer or the government, but the welfare cost on the potential welfare cost on the policy recipients can be large. And understanding the welfare implication definitely will inform the policymakers if, of course, they care about the social total utility or they care about the distributional effect in terms of welfare, right? So as the papers I listed here, you can see they're all very new, and the two studies that are most relevant to the current study here are the one on social comparison type of nudging and the other recent working paper on social recognition type of nudging. In the current paper, we kind of aggregate the two types of welfare analysis in the two papers, and we look at a specific intervention, nudging intervention, that is to provide rank information to improve performance. I would argue, of course, the rank information has the social comparison component, and depending on how the information is provided, it can also invoke social recognition component of the utility function. And rank information provision is very common in the real world. As I listed examples here, you can see a lot of them in the business world. Sometimes the rank information is provided standalone, sometimes combined with financial incentives, that is piece rates, wages, or tournaments, right? And sometimes the bonus is symbolic, sometimes it's promotional incentive. And it's also very common in the public sector as well as in education. And there has been a lot of experiment evidence, either in the lab or in the field, showing that providing such rank information does improve work or academic performance. So in today's paper, we're going to look at the welfare aspect of providing rank information. And by nature, rank is a positional good. So it's an open question whether the pride or utility the top performers receive can really compensate for the shame or disutility the bottom performance receive. And to see that, we conduct a lab experiment, and in the experiment, subjects just conduct a very simple cognitive task. It's multiplying two-digit numbers, and there are 3 rounds in total with a fixed pay. We adopt a fixed pay because we want the rank information to be purely about performance, relative performance, instead of relative income or relative expected income, all right? And we also provide a hypothetical motivator. We told the subjects, suppose you're an employee of a company, even though you are paid a fixed amount, just suppose the more correct answer you get, the higher your company's profit will be. Okay, and as the core part of our research, we look at 4 types of information feedback. Type A, so no rank information. So in the end of the in the end of each round, in the end of the round, the subjects just see the total number of correct answers she got, and then B, we provide private rank information. So you learn your rank within the session after the round. And then type C, we add on top of the private information, a partial public announcement of the rank. So only those among the top third, their rank will be announced in a face-to-face situation. And then type D is full announcement of the rank. So everyone's rank will be publicly announced. So I will refer to these treatment feedback ski types A, B, C, D, and they are as shown here. So this is how the experiment proceeds. We first do a face-to-face ID calling because we want the subjects to get an idea about how the announcement will be later when they are facing the announcement or making choices. And then went back to the computer lab, conduct the first round of the task. We did not tell them anything about the information feedback in the first round, but afterward, we feedback them with type A feedback, that is only the absolute number they completed. Then before round 2, after round 1, they make 6 sets of choice questions together with willingness to pay questions. And I will talk about those questions in more detail later. And we use the BDM mechanism to incentivize the choices and the WTP questions. So basically for a positive probability 1/5, the round 2 and round 3 feedback scheme will be decided according to one randomly chosen subject's answer to one randomly chosen set of questions, and the WTP number will be compared to a random number, and if the WTP is bigger than that, the feedback scheme will be implemented according to the chosen one of the randomly selected subject, and if the WTP is smaller than that, it will be randomly decided, and that's typically how the BDM works, right? And then we conduct round 2. After that, there's an ID calling. And if it is feedback scheme C or D, there will be either partial or full rank announcement. And then round 3, and again, the ID calling again. So more detail about WTP questions. So we ask them 3 times 2, that is 6 sets of questions. So we ask both unconditional and conditional WTP questions, and we ask them to choose between A and B, then B and C, and then B and D. So I know this is in Chinese, but I just want you guys to see how these questions are formatted. So this is an example of the unconditional question, between A and B, which do you choose? And then the second question asks, from the 300 points, which equals 30 yuan, how much are you willing to pay to guarantee that between A and B, your chosen one will be implemented? Okay, and then the conditional WTP questions are very similar, except for we have multiple sets of them, conditional on the rank. So if you rank number 1, which do you choose, and what's your WTP? Okay, I'll pause a little to see whether there are any clarification questions. Okay, so then this is how our experimental sessions break up. Because we have this BDM, so only for 1/5 of the sessions, we have endogenously decided feedback scheme. And for the other 4/5, we exogenously vary the feedback scheme according to our ABCD 4 types. And we also vary the number of people. And in that sense, then the possible rank in the conditional WTP questions will be slightly different depending on the session size, right? So, and we conducted the experiment in Nankai in Tianjin, China, and it took less than 1.5 hours, and the subjects received an average of 58 yuan, including the show-up fee. So to kind of guide our empirical analysis, we developed a very simple theoretical framework. So we assume that under type A, so when there is no rank information, we first of all assume that an individual's utility is linear in income, quasi-linear income, and then we assume this G function to capture both the cost and the psychological benefit of improving the performance, which we denote with P. So the cost is, of course, the effort, and the psychological benefit, you can think of it as many things. And one example is you can think of it as the warm glow utility of working hard for this hypothetical company. And I don't think it matters that much what this psychological benefits part is in this G function, but we assume the G function is single picked in P. And then when we provide rank information privately, we assume this invoke the social comparison utility, which we use the K function to denote. And it's a function of R, the rank, which of course is decided by by one's own performance and others' performance. And then type C and the D feedback scheme, we assume that with the public announcement, this additional R function, we use R1 and R2 for the partial and the full announcement respectively. So these social recognition functions will also be invoked. So to map those utility terms to our WTPs elicited in the experiment, for the unconditional ones, the unconditional WTPs will correspond to 1/2 of the difference between the indirect utility between two different feedback types. And for the conditional ones, the conditional WTP will correspond to 1/2 of the K function or the R function. Conditional on R, of course. Okay, so to step back a little, so the total social utility change, delta W, can be divided into the social welfare change because of the behavior change, or in our case, performance change, and those because of social comparison and the social recognition. We can call them pride or shame if you want. As I was saying, our unconditional WTP give us a direct measure of this total delta W, and the conditional ones will help us identify the second term, the pride or shame, part of the social welfare change, which we follow the literature, we call them the net emotional effect. Okay, and actually this total change in W, the delta W, can help us with cost-benefit analysis, because if you imagine about it, if you can put a monetary value to improve the performance, then you can compare that to delta W that is borne by the policy recipients or the workers, then you can see whether this is really good or bad, right, in terms of total social welfare. And the second part here, the net emotional effect, can be used to guide us with cost-effective analysis. The reason is we can assume, or according to our basic assumptions, the financial incentive that you can interpret it just as piece rate wages, they will not incur any this type of pride or shame utility changes. But if we can then measure these parts, then we can compare the social comparison or social recognition type of interventions to the purely financial incentives, right? Okay, so here are the reduced form results. So in round 1, we didn't do any treatment yet, so the balance is quite, so the baseline is quite balanced. And round 2 and 3, you can see the performance does improve a little in C and a bit more in D. And these results are not very significant, but if we put them into regression, especially after we control for the round 1 performance, we can see especially the dummy D, treatment D does have a quite significant effect on performance. And here we construct this dummy using whether the baseline performance is above or equal to 7, which is around the average number of correct answers. And then you can see in column 3, the interaction terms are all negative. So this means the rank information mainly works on those low performers in the baseline. And if we look at the conditional WTP, so what we did here is we feed a quadratic relationship between the conditional WTP and the rank, and we allow heterogeneity for the top performers and the bottom performers in the baseline. And we can see, as you would imagine, the slopes are basically negative. So the higher you rank, the more you are willing to pay to learn about this rank information. And there's a slight difference between the top and the bottom performers. But so if you look at it, so most of the points are above 0. So even just by eyeballing these 2 lines and their relationship and their positions, we can kind of get a general idea, like on average, people are willing to pay to receive the ranking information privately. What about the ranking information publicly announced? So between B and C, it's kind of surprising for the top performers. The line is actually increasing. But again, and the top and the bottom performers, their patterns are different now. But again, for most of the points, they are above 0. So this kind of gave us a general idea. Also, people are willing to have the public announcement of at least of the top performers. And if we look at B and D willingness to pay, then a clearer heterogeneity pattern shows up. For the top performers, it's mostly a horizontal line, and for the bottom performers, it's a straight line that goes across this 0 versus 50th percentile point. So, and you can also see this slope have this line has a slope that's flatter than 45 degrees. So that means for the top performers, they kind of don't care if the rank is publicly announced or not. But for the bottom performers, if they're if they're ranking above the median, they're happy. But if they're ranking below the median, then it will hurt them. But the extent of the hurt actually is smaller than the extent of the happiness the high ranking will bring. So in that sense, on average, people also are willing to pay to get this to get this full announcement of rank.
You have 4 minutes, including questions left.
Okay. So with structural estimation, we will be able to provide more accurate estimates. So what we did is we follow the literature. We give the G function and K function specific functional form assumptions, and then we identify the parameters with different moment conditions. By now, the results are quite preliminary because we use a step-by-step GMM, but later we will adapt to more efficient GMM method. So what we did is we used the estimated parameters from the structural estimation, and then we calculated everyone's performance, and then we ranked them. Then we're using the rank for the whole sample. Everyone has that rank under every feedback scheme, right? And then we plug them into the SC or SR functions, and we get estimates of this net emotional effect. So to read this table, as I said, this can serve cost effectiveness analysis. So if the policymaker's goal is to reach the performance level under feedback B, then B is better than A plus some piece rate wage. And if the objective is to reach the performance under C, then C is better than C is better than B plus financial incentive, and which is better than A plus financial incentive. And the second row shows if the objective is to reach the highest performance that is under feedback scheme D, then D is worse than C plus financial incentive, but D is still better than B plus financial incentive, which is better than A plus financial incentive. Okay, and then the last thing we did is we also put the structural estimation back to calculate the total social welfare change. And as I said, the unconditional ones directly give us estimates of this delta W, the total social welfare change. And if you compare the two columns, you can see the unconditional WTPs are more extreme, both on the positive side or on the negative side. So so in this case, it won't be able to be explained by overconfidence alone. So maybe there's also probability weighting. To conclude, if the policymaker comes to us to ask for recommendations, if the objective is to maximize performance, then our recommendation order would be DCBA. But if they only care about the workers' welfare, they don't care about the performance, then it will be CBDA. And if they care about the total social welfare and say their goal is to reach the highest performance that is under D feedback scheme, then we recommended C plus financial incentive, then D, and B and A. Okay, I'll stop here to see whether there are some questions, and there are some discussing points. I think maybe the audience will pick up some of them.
Yes, so there is a question by Ling Su. I would unmute you, and then you can ask the question directly. If there are other questions, just write them into the chat. So Lin, you can ask.
Okay. Yeah, thank you, Wen, for the presentation. My question is about when you providing the public ranking information, do you consider the social distance the relationship among the participants when they consider public ranking, because it could be a factor and affect people's behavior towards public information. When these strangers or co-workers.
Yeah, that's a very good question. So we do have this question in the post-experiment survey asking how many acquaintances and how many friends there are in this session, and we did find it has a heterogeneous treatment effect on performance, but we didn't find it has heterogeneous treatment effect or heterogeneous effect on WTP, conditional WTP. So we're kind of wrapping our head around it, and also the structural estimation where we're kind of starting with the simple specification, but later we'll definitely consider about including the number of acquaintances or friends into our analysis. Thank you. Yeah.
Okay, thank you.
20 minutes are unfortunately up, so we have to switch to the next speaker, which is Karen. So thank you, Vanbo, and sorry for the short time, but that's what we have. So Karen, can you share your screen?
Sure.
Okay, I can see it at least, so full screen maybe, and then you can start when you're ready.
There?
Okay, yes.
My full screen now? Yeah.
Yes, go ahead.
Okay, thank you. So I'll talk about culture and gender differences in willingness to compete. And this is joint work with my colleague Andreas Kotsadam, which works at the Frisch Center with me, and Anine Rige, who is a postdoc in psychology at the University of Oslo. So why doesn't it want to? There. Okay, so previous literature has shown us that there are gender differences in competitiveness and that they are large. So the willingness to compete between men and women differs. And also there is some evidence that the willingness to compete is correlated with educational choices and labor market choices. So this is something that seems to be important preferences. So men and women have different preferences, but these vary by context. And there are two opposing theories on gender differences in preferences and the macro level gender equality. So the first hypothesis is the social role hypothesis, which states that gender differences will diminish as the view of men and women's roles become more equal. And the second hypothesis is the resource hypothesis, that says that as more resources allows more gender-specific ambitions and goals, and therefore will lead to an increase in gender differences. And for instance, Falk and Hermle find in 2008 paper that gender differences in preferences is more equal. It's in more gender equal countries is larger. And this also relates to the discussion on the paradox in personality and labor market segregation. So back to culture. So cultural factors may be important for competitiveness. And there are, especially some seminal papers by Gnisi and co-authors, looked into and compared two different societies. The Maasai society in Tanzania, which is a patriarchal society, and the Khasi society in India, which is a matrilineal society. And they found that in this patriarchal society, men competed more, while in the matrilineal society, women competed more. And this has been interpreted as cultural differences affecting the gender gap in willingness to compete. But there are other studies that compare two countries that find the opposite relation And there's also a study from Congo that looks into different groups within Congo that are matrilineal and patrilineal. And when looking at all these groups, they don't find any difference in the gender gap in willingness to compete. That's related to matrilineal and patrilineal societies. Okay, so what the approach that we will use is the epidemiological approach. And this approach identifies the effect of culture by comparing the outcomes of individuals living in the same economic and institutional environment, but whose cultural beliefs, norms, and preferences are potentially different due to their migration histories. So what we will do is that we will compare Norwegians whose parents were born abroad and investigate how the cultural influence of their parents' home country influences gender differences in willingness to compete. And we follow Fernandez and Fogley, and we use the female labor force participation in their parents' home country or country of birth as a proxy for ancestry culture. So the ancestry culture originates in the parents' home country and is transported to Norwegian into Norway with migration, and then is then reproduced within families via childhood socialization. And most importantly, when we then look at the behavior of people that are born in Norway, but whose parents' culture differs, then we separate the culture from the institutions that caused them. And we also use an extended version of this epidemiological approach, that we compare women and men from whose parents are born in the same country. So we look at, and then by doing that, we control for other factors that parents pass on to their children, such as human and economic capital, would be similar for men and women. And that would also control for differential selection of different immigrant groups and non-gender differences in ancestry characteristics, for example, economic development. Okay. Are there any questions or now? Clarifying questions? No. So what we do, we use the classical competition experiment by Nidle and Westerlund, but we do it online. And in our experiments, there are 4 parts. So in part 1, there's a task that they perform, which are a paid piece rate. So they get 5 Norwegian kroner per task. That is correct. In part 2 of the experiment, there's a tournament. So then the best player in a group of 4 earns 20 Norwegian kroner. In part 3, participants can choose between the piece rate or a tournament. And this will be our main outcome for willingness to compete. And in this part, they compete against the part 2 performance of the group. And finally, we have a part 4 where they answer some survey questions where they are paid between 25 and 50 Norwegian kroner. Then one of these parts are chosen for payment, and all participants receive a show-up fee. So this is the task that they perform. Since we have an online experiment, instead of using perhaps the most common task, which is multiplying numbers in these competition experiments, we use this task, which is counting. They have to count numbers of ones in these matrices. So the reason why we use this is that online it will be less possibilities of cheating by, for instance, using a calculator, because we don't have that much control as in a physical lab. And this also has been used in other experiments, finding similar gender differences and in competition, but it is gender neutral with respect to performance. So they solve as many tasks as possible in 90 seconds. Yeah, and the competition group that they compete against is 3 randomly selected participants from a pilot. Okay, so our population and invited sample. The population that we're interested in here is people that are born in Norway between 1980 and 2000, who have at least one parent that is born outside of Norway. So we choose, so the parents are born in one of 59 different countries that has most immigrants in Norway. And then we invite a random draw of 200 people from each of these ancestry country backgrounds to participate in an online experiment. Yeah, so Norway isn't that big a country. So for those country backgrounds that there were less than 200 people with parents born in that country, we got to invite everybody. So the smallest group that we have in the experiment is that it's from Afghanistan, there was only 31 women. So 31 women that the population register could provide us with information about, and that have 1 or 2 parents born in Afghanistan. So to increase power, was there a question?
No, not in the chat. So nobody wrote something.
Yeah, I'll come back to that later. So in order to increase power, we oversampled in the tail of the female labor force participation distribution, which is, well, I'll come back to why we use that, which is our main measure of culture. So we oversample from the 3 countries in the upper tail. So the 3 countries with the highest female labor force participation, which was Sweden, Denmark, and Vietnam, and the 3 countries in the lower tail, which was Pakistan, Somalia, and Iran. So that was, we oversampled who were invited, and our final sample consisted of 1,943 individuals who live across Norway. And neither the invited sample size nor the final sample size from our country was correlated with our measure of culture. So our main variable is, the main dependent variable is whether the participant chooses to compete or not in part 3 of the experiment. And our main measure of culture is the logged female labor force participation in the parent's home country in year 2000. And the female labor force participation is defined as the percentage of female population aged 15 to 64 who are currently employed or seeking work. And we use the World Development Indicators Online as a source for this. We also have an alternative measure, which is the World Economic Forum's Gender Gap Index. Okay, so just a quick look at female labor force participation. So what we see here is that in general, it correlates with a lot of other measures of gender equality. So it's positively correlated with our alternative measure of gender equality, and also with the female labor force participation in 1970, and women in politics and the gender attitude scale from measured in the World Values Survey. So you might wonder why we chose the year 2000 and not 1970, as the parents probably lived in their home country, was much more similar in 1970 and then 2000. And the reason is that in 2000 we have data on more countries. And also as there's a strong correlation, we think that that is a better measure. In addition to the data that we get from the experiment, we have data from administrative register data, which we get from Statistics Norway, on gender, education, family background, earnings, income, and parents' education and earnings, which allows us to look a bit more closely at selection into our experiment than many other studies are able to. So our study was registered beforehand. So shortly, our hypothesis is that we first of all want to try and replicate that women compete less than men, which is found in the literature. And we also want to look at whether this ancestor country FLFP affects the willingness to compete among women, and secondly among men. And then thirdly, most important, whether the gender difference in willingness to compete is affected by the female labor force participation in the parent's home country. So to the results. So first of all, I'll just look at the performance in the counting task. It's important that the performance actually is equal between men and female in this, men and women in this task, and it is. So if anything, so the difference between men and women is not significant, but if anything, women are on average slightly better, but not significant. So if we look at the distribution and performance, we also see that it's very similar between men and women.
You have 4.5 minutes, including questions.
Okay, so then the gender difference here, we see that we replicate that women compete less. And then when we look at the relation to female labor force participation, we see that women whose parents are from more equal countries, they compete more. When we look at men, we see that men whose parents are from more gender equal countries, they compete less. So if we, did you say 1.5 minutes or left?
In 2 minutes, the questions should start.
Okay,
so 2 minutes for presentation.
So I'll just jump to the graph here, which I think visualizes it a bit better. So here we see the log FLFB here and the bin scatter. So for each of these points is the average of one bin. We see that for women, the willingness to compete increases with the gender equality in their parents' home country, while for men, the relationship is opposite. So for countries where the gender difference, where less females work, the gender difference is larger, while in countries where more women participate in the labor market, then the gender difference is lower. So we then also look at how we had some questions in our survey of for instance, about gender equality. So we want to look at whether it seems as our participants have internalized some of the values of their parents' home country. So we include some of the same questions as in the World Values Survey. And here we see the correlation. So here we see that the gender attitudes that our respondents provide is correlated with the gender attitudes which are reported in the World Values Survey in the parents' home country. And also for other variables that we included from the World Values Survey, we see that this is correlated, which we think supports the idea that our participants have been have received some cultural impact from their parents. So what we also do is that we go into other alternative explanations of why we find this relationship between parents' home country and willingness to compete. So we look at whether risk or confidence can explain it. We look at factors in the ancestor country level as education, religion, GDP, and we also look a lot into selection into our experiment. Although we, in all these robustness analysis, are results of female labor force participation's effect from the parents' home country, effect on the willingness to compete is robust. So to conclude, then we have done a pre-registered competition experiment with a large sample of Norwegian-born individuals, and we find that the gender gap in willingness to compete is lower for individuals with parents born in more gender equal countries. And this lower gender gap is driven by both genders. And then we also find positive correlation between gender attitudes reported in this survey and answers reported to the same questions in parents' home country. And we think that suggests that there's cultural differences are transferred from parents to children, and that this matters for gender attitudes. Yeah. And
okay.
we also have looked into some selection, but I think I'll stop there.
So thank you. So we would have time for one question. If there's one, just write in the chat and then I can unmute you if there's a question. If not, we can already switch to the next speaker. So Isa, maybe you already get set up with your slides. If there's a question in between, just write it. We can use the setup time.
Yeah, if Karen stops sharing the screen, I will share mine.
Exactly.
Thank you.
Okay. So there was no question so far. Okay, so thanks again, Karen. And then we have the next speaker, which is Isa on, yeah, you will see. You can start.
Thank you. So today I will be talking about all-pay contest, in some sense an environment with competition, and with this respect it fits to the session. And I will be talking about effort provision and optimal price structures in contests when the players are expectation-based loss averse. So contests or tournaments are environments that we see quite a lot around us. So in a lot of competitive environments, basically, like in organizational settings, we see employees competing for promotions or bonuses, or in sport contests, we are seeing athletes competing for medals, or also big monies, like in tennis tournaments, or in R&D races, we are seeing that research teams are competing with each other to win awards. And in all these examples that I give, effort is always costly. Either you are competing in an R&D race, even if you don't win the prize, at the end of the day, you spend your time, you spend your effort and resources, and that's very costly for you. So that the decision on how much effort to put is actually something that needs to be carefully thought. And another important thing is actually in these contests, how to allocate the prizes, right? And this depends, of course, on the objective of the designer. So it might be that you're trying to motivate the top player, the top guy, or maybe you are trying to motivate everyone as much as you can, or maybe the worst guy, yeah. But the first one who asked the question of how we should allocate our bonuses was actually Galton, and back in 1902. And in his famous paper, he asks basically, okay, if we have like 100 euros to divide into two prizes, how should we do it basically? Should we do it like 100-0? Should we do it like 50-50 or 70-30? And that was the first time that such a question from the perspective of a designer was asked, as much as I'm aware of. And there has been many other papers working on this, of course. The important thing is that in this question, Galton didn't specify like the target. Yeah. If we say that the target is to motivate everyone, so that, for example, if you're in a workplace, you are trying to motivate all your workers, or if this is a sports competition, again, you want all the athletes to put the most effort they could to make it more competitive and more attractive for the watchers, then actually a well-documented fuzzling phenomena that we observe is between the theoretical predictions and the empirical observations that we see. So basically what we see is that, and by these empirical observations, what I mean is like lab and field experiments, and also causal empirism, if you like. And what we see is that there are some players who are like workaholics, who basically overdo it. And these are the guys who have high abilities. So these high ability guys have lower costs, right? And we see that there is also some dropouts. Basically, some contestants or some players, I say, okay, you know what, I'm not even in, I'm putting zero effort. And we see this mainly with low ability people who are either putting very little effort or they're just withholding themselves. And this has been reported in several different papers, either in lab experiments or field experiments. And also with causal and prism, we can see like workaholics and dropouts at work, also dropouts at college, or sometimes self-handicapping at workplace. Then the question that I'm asking is, okay, so this observation, basically this departure from the theoretical prediction, raises two questions. First of all, what is the driving force behind this observation? That why do we see this bimodal behavior? And how can we reconcile the theoretical predictions with this observation? And the second question that I'm asking is, what is the implications of this observed prediction from the perspective of the designer? Because clearly in the theory, the designer, when calculating what is the optimal incentive scheme, he assumes a certain type of behavior, but the behavior that we are observing in experiments or in the field is different than the one that's assumed. So then probably it might be the case that this observed behavior may have some implications for the bonus allocation from the perspective of the designer. So in this paper, what I do, this will be an applied theory paper. What I do is I study multiple price contests with expectation-based loss-averse players. So basically then what I'm saying is, okay, you know what? Actually, this might be because actually people are not risk neutral, and it might be just the preferences that they have. And I'm proposing that, okay, let's assume that these people are expectation-based loss-averse, and we have a lot of evidence about this in the literature that in competitive environments, actually people do have this type of preferences. Then what I show is actually the model is able to reconcile all these observations that we see empirically with the predictions, the theoretical predictions. So basically then the theoretical predictions becomes aligned with the observation, kind of this bimodal behavior. And what I also show is that the optimal incentive mechanism also changes, that putting multiple prices becomes optimal, even even in the case where standard preferences are predicting the optimality of a single price. So for the sake of the time, I won't really talk about the evidence about loss aversion or the literature, but I will just dive into the model and give you a little bit of flavor of the findings and the intuition behind it. So basically, I'm generalizing the contest model of Mode 1 and Cella. This is pretty conventional model where the contest designer has a fixed budget sum, let's say this €100, and he decides how to allocate this €100 into bonuses or prizes to maximize total expected effort. So basically he wants everyone to work as hard as they can. So basically he's putting effort for, his aim is on everyone, not like the top or the bottom player. And in the second stage of the game, given this price structure, then the contestants, the players, are simultaneously undertaking efforts to win these prizes. And these contestants have private information there about their abilities. So basically I know the distribution of the abilities in the population, but I only know my own type as my private information, which in turn affects my cost of effort. So in the paper, I concentrate on the most general case, but here for the sake of easiness, I will only concentrate on a special case with two prices. So let's say that the designer can put at most two prices, where V1 is the first, V2 is the second one, and they are, are larger than 0, and sum up to 1. So basically, I'm normalizing the 100 to 1. And let's assume that there are two contestants at least, so that we are in a non-trivial case. Then each contestant has an ability parameter CI, and these are IID and private information, so everyone knows their type on their own, but basically they also know the distribution, but not the types of the others. And then they're taking costly efforts, which is XI, and the cost of effort will be depend on my type, of course, because if I'm a high type, it will be less costly for me, and it also depends how much effort I put, right? Because if I'm working days and nights, of course, the cost will be higher for me. And here, this gamma is the cost of effort function. It could be either increasing, it could be either linear or convex or concave, okay? So the timing of the game is as follows. The designer knows the price structure, the number and the level of the prices. The nature determines the abilities of contestants, and I know my type. And then the contestants are simultaneously putting efforts to win these prizes. So the payoffs are the contest designer gets the sum of individual efforts that he's trying to maximize, And the contestants are like the one with the highest effort wins the first prize, and the one with the second highest effort wins the second prize, V2. But everyone pays the cost of effort, regardless of winning anything or not. And I briefly would like to talk about the Kosei-Rabin model, where basically the intuition behind the model is, okay, we have this consumption utility, the intrinsic utility that we always have, but on top, we have the gain-loss utility part. Okay, that's like the logic of it. And this gain-loss utility part is giving this loss aversion sensation. So basically what we see in this picture is the winners of a gymnastic final. And this lady got the silver, the second best prize. She looks happy, but actually she was pretty upset because she just lost the gold one. Okay, so basically our expectations really matter in our happiness. Even if you end up with the silver, you might be really, really unhappy about this at the end, if your expectation was winning the gold. Then I would like to talk briefly about the utilities. So in this situation that we have, let's say that people have, there are these two prizes and more than two contestants, then the probability of winning the first prize is P1. Let's denote the probability of winning the second prize by P2 and the remaining probability for not winning any prize. Okay. Then while constructing the utility, basically I will first consider winning the first prize. In this case, there is this consumption utility, right, where I won the first prize and I'm paying the cost for my effort. And then there will be the gain-loss utility. And in this gain-loss utility is characterized as follows. Basically, I'm comparing myself to all the possible outcomes, my actual outcome to all the possible outcomes, and I'm seeing whether I'm in a gain or a loss. So basically, with P2 probability, I could have won the second prize, but I ended up with the first, so I'm in a gain domain. That's perfect for me. So then I perceive this difference between the prizes as a gain, and with this probability, I could have ended up with nothing, and then the difference between the first and nothing is the gain that I realize. If I am considering the case of winning the second prize, again, there is this consumption part, and then the gain-loss utility. And here, actually, we see that the player is in the loss domain. Why? Because with P1 probability, he could have won the first prize, but he ended up with the second. And the difference between the two prizes, he perceives as a loss. Okay. And then, basically, the player makes all the possible comparisons, just that I will not go deep into details with everyone. With every term. And then the expected utility is going to be the probability of winning the first prize times the utility of winning the first prize plus the probability of winning the second prize times the utility of winning the second prize, and so on until all the cases are covered. So basically what we are doing here is a double integral, if you like, right? So the outer integral is giving me the expected utility, and the inner integral is making the integral over the reference point. Okay, and let's remember the problems that we have at hand. The first is contestant's problem. Knowing the price structure, the contestant is supposed to choose the effort level, and then we will go one step back. So this is solving by subgame perfection. Then we solve for the designer's problem, where given the optimal behavior of the contestants, now how should the designer allocate the prizes? And for the first problem, I will just illustrate this in an example. I'm not going to go into the details of the equations. So basically, let's assume that there are two prizes and these are equal, 0.5, 0.5, okay? And let's say that the loss aversion degree is at moderate levels, but it's smaller than 1, yeah? And the abilities of the players are distributed by a uniform distribution over the interval 0.5 to 1. Then what we see is that in these three different graphs where the cost function can be concave, linear, or convex, actually the shapes doesn't really vary too much. And what we see on the y-axis is the effort, and the x-axis is the type, and the black line is the prediction of the theory, and the blue line is the standard theory. And the blue line is the prediction of my model, where there is loss aversion on the part of the players. Then what we see is indeed these high ability guys are overdoing it and low ability guys are underdoing it. And this is like the same in all these three graphs, but of course in theory in general this is also the same. right? And the intuition behind this is high ability contestants are thinking that, you know, they already have a ex ante very high expectation because they know their side. They say, okay, you know what, I'm one of the best. Probably I'm gonna win this thing. So then they're putting more and more effort to avoid the loss sensation in case they lose. Okay, and for the low ability people, it's going the other way around almost, because they think that they're going to lose almost for sure, and they try to avoid the feeling of losing as much as possible, and that's why they're basically they try to reduce uncertainty, and that's why they're reducing their efforts. And if I take the analysis, if I take exactly the same analysis but just increase the loss aversion index a bit more, which is still plausible but larger than 1, then what we see is that there is a mass of players who are just dropping out. They're putting 0 effort. Okay, now what's the logic behind this? For these people, actually, when the loss aversion degree is sufficiently high, and what's sufficiently high is larger than 1 in this case, for the low ability players, the expected utility becomes 0, because then the gain-loss utility in their expected utility is dominating the consumption utility. So their loss sensation is so much that to avoid the negative expected utility, they put 0 effort and at least guarantee themselves the 0 expected utility. That's the reason why they are dropping out. And this is a bit in line with sort of self-handicapping that we know from psychology. Given that the behavior from the contestant side, of course, in the paper I showed that this is the most general case and I prove that this is the behavior, but here I'm not going to do that. But rather I will discuss the designer's problem. So given the behavior from the contestants, then how should the designer allocate his prizes? First of all, how many prizes to put, 1 or 2, and the magnitudes and ratios of these prizes. Okay.
5 minutes including questions.
Yeah, in order to maximize the total expected effort. And solving out the designer's problem, what I find is that, so I summarize it in this paper, table, where on the left column, actually I have the types of the cost functions, linear, concave, or convex. And in the second column, this is the predictions of the standard theory, namely risk neutral players, where there is no loss aversion. Yeah, so this is the prediction of the AR paper of Moldova and Sela. And here on the last column, I summarized the predictions of my paper, where there is a loss aversion. So one very strong difference between the predictions is that in the Moldova and Sela paper, the results are independent of the number of players, of the ability distribution, whether they are very, you know, like a normal distribution or a skewed distribution. The results are independent of any parameterization. So basically they show as long as the linear, or as long as the cost function is linear or concave, then it's optimal to put a grand single prize and that's it, right? Where they find the multiplicity of equilibria is only when the cost function is convex. And what I find in my paper is that actually the results depend very much on the parameterization that we have, how many people we have, and etc. And what I find is that even in the linear cost of effort function case, it might be optimal to put more than 1 prize. And very briefly, I would like to describe the intuition behind it, and then we have 1-2 minutes for the questions. So basically, the intuition is that imagine that we have 3 people, and in another scenario, we have 100 people, right? In a 3 people scenario, if my ability is not so high, I might still dare to put a bit effort because there are only 2 competitors of mine. There is still some fair chances that I'm going to win the prize, right? If there's a grand single prize. However, if there are 100 people, then I have 99 other competitors, and I know that my type is not really very high. And I think, you know what, there is this 1 prize, and there are 99 other competitors that probably are not going to win this, and I stay out or I put very little effort. However, if the designer, instead of putting a grand single prize, puts 2 prizes, then basically, as this low ability person, I may say, you know what, there's the second little prize, and I can still compete for that one. And then I start to put a bit more effort, basically. So then the second prize is actually kind of motivating the lower ability people, and the first prize is motivating the higher ability people. And all in all, then this is increasing the total expected effort. Okay, and this is like the logic that it depends on the number of people, and it depends also on the ability dispersion. Yeah, there are still some ranges where it might be optimal to put a single price, of course, but this, as I say, depends on the parameterization that we have, and also depends on the loss aversion index, basically how much loss averse our players are. And just to wrap up, so in this paper I presented an applied theory piece where I'm working with multi-price contests in the presence of expectation-based loss aversion on the side of contestants. What I show is that I provide a backbone for the observed behavior, theoretically, and I also show that when players are loss averse, indeed the optimal incentive mechanism is changing quite a bit, and multiplicity of prizes becomes optimal. Thank you, and I think I'm going to stop there, and we have questions for 1 minute, I think.
Exactly, yeah, thank you. So there is time for questions, or at least one question. So if there is something, write in the chat, I can unmute you. So, anyone? Okay, so I don't get a message yet.
Okay, then maybe in the meanwhile I stop my share so that
maybe you can already get set up if there comes a question up. Otherwise, we can go on.
Yeah.
Okay, so thank you again for this interesting talk, and then we continue with the next one by Arthur. Can you share the screen? Does it work? Yes. Okay. Okay. And then unmute yourself, and then you can. So your microphone is still muted.
There, that's better.
Okay, so go ahead.
Do you see this full screen now?
Yes, yes.
Okay. So this paper is one of a series of papers that Clarita, Jordi, and I are doing on this status ranking. And this one, we bring a lot of different elements together. So our point of departure is that one thing that people often overlook when they're talking about competition, especially competition about gender, is that it consists of two elements. On the one hand, there's a rivalry for resources, right? So if there's a vacancy for a position at a university, right, only one person can get that position. The resource is the position, and there's a rivalry to get that position. And on the other hand, there's a ranking of relative performance. You know, whoever gets that position is somehow deemed to have a higher status than whoever does not. Now, this can be a private ranking that only you know that you applied, but sometimes it's also public, right? There's a lot of talk going around about who applied and who was on a short list, etc. So Gnesi and others, and hundreds of replications, have shown that women underperform compared to men on the rivalry. And last year in experimental economics, we showed that even when there's no rivalry, women underperform on the status ranking. Now, in this paper, we ask, are rivalry and status ranking substitutes or complements? So do they reinforce each other or do they replace each other? We do that in study 1. And then we ask, that should be a Roman number 2, what mechanisms underlie gender differences? So which mechanisms can explain? And for that, we have some element from the first study, and we have 3 extra studies. But for the experimental design, we use the following general setup. In every treatment, there's going to be 2 parts and typically involve 3 types of players, A, B, and C. The C are passive, they play no important role. You'll see in a second. In part 1, A's and B's work individually on a gender-neutral cognitive task. Gender-neutral is that we know that when they just do an isolation, the performance of men and women is more or less equal. The task consists of, maybe you've seen it before because we've used in a lot of papers by now. There's 2 matrices with 100 numbers, 10 by 10. They're 2-digit numbers. You have to find the highest number left and the highest number right, and you have to add them up. That's all. Now, A's in some treatments receive feedback And in some treatments also have to report to C. That is C's role. C is a participant, a peer, sitting in a different room, and A's have to go there and tell them how they rank amongst the group. So C basically plays a role of some kind of social ranking. B's don't report to anybody. Then we have 3 treatment dimensions. One is rivalry for resources or not. When there's no rivalry for resources, there's just a piece rate payment. As usual, people get €1 per correct solution. When there's rivalry, there's a group, out of a group of 6, 2 people each get €3. The top 2 performers in terms of the number of correct summations, each will pay €3. This is very standard. This way of comparing rivalry to piece rate has been done many times. Second, do we tell people their own rank in the group or not? That's the second treatment. And third, is it public or social, this ranking? That is, do they report to the C player? So is there some person who can actually compare the ranks and compare people with the ranks? Now, if you go to someone and tell them your rank, then you also know your own rank. So you cannot have public status ranking without private ranking. And for that reason, we have 6 treatment cells in total. So what's the experimental design of study 1? So common features are C players in separate rooms. They don't know what the task is. They just are told that a low score is better than is worse than a high score. The A players are the ones that might be socially ranked. Before they start the task, they first go to the C player and they say, I'm going to come back later and tell you my score and rank. We do this so that they really know that this ranking is going to take place. And after they've done the task, they go again to the C player, one at a time, but to the same C player. And then they report, my score on this task was 10, and I ranked 2 out of the 6 players. So these experiments were run at the University of Bologna and Bless Lab. For study 1, we had 432 participants. There were 34 sessions. A typical session would have 6A and 6B players. I don't know why it says average, that should be B players. Sorry about that. The earnings for A and B players were on average, that's where the average comes from, 1796. That includes a 5-year, and C players just got a flat fee of 15. Remember, these C players had a very boring role. They were sitting alone in a separate room. They had to wait for someone after the instruction to come and say that they're going to come back. And then they had to wait while people were doing a 15-minute task. And then people would come in and say something, and that's it. And this took about 1 hour, 15 minutes. So what did we observe in this first study? First of all, when there's no ranking, men perform slightly better than women. That's coincidence. It's not significant. When there's rivalry for resources, men perform much better than women, and this is significant. So without rivalry for resources, there's no gender difference. Now, we predicted no gender difference. So to test this, we had to do some Bayesian analysis. And with this Bayesian analysis, a model that predicts no gender difference is three times as likely to be correct than a model that predicts a gender difference. The details are in the paper, but so the bottom line here is, because our hypothesis is no effect, we cannot do a standard test. We can do a standard test for the rivalry case, because there we predict there will be an effect. And we find indeed, like Denise et al., that using permutation t-tests, that with a very, very high likelihood, we reject the idea that they would be equal. So we find support that rivalry makes men outperform women. Okay, so we go move from here to here, and we added social ranking. So what happens when there's social ranking? So when you have to go to a C player. Well, the first, without rivalry, which is what we did in our 2019 paper, we again find, so we replicate that result with a new subject pool. that social ranking makes men outperform women. And again, this was predicted, so we do a standard test and we find high significant result. And we find also that if there's rivalry and we add social ranking, then also, this not really replicates because we didn't do the rivalry case in the other paper, but we do replicate the fact that social ranking matters. So under social ranking, men outperform women. And you know, notice these p-values, right? All these p-values are much more significant than even at the 1% level. So this effect really exists. So what we added here is we also considered private ranking. So with private ranking, you know your rank, but you don't have to report to anyone. And it looks like from the figure, right, over here and over here, that men outperform women in these cases too. And that's the case, again, highly significantly. These permutation t-tests show that even private ranking makes men outperform women. Okay. So what do we conclude from this? Any type of ranking or rivalry creates gender differences. And if there's no ranking and no rivalry, there are no gender differences. The question that this then raises is, are status ranking rivalry complements or are they substitutes? So if I already have ranking, I add a rivalry, right? Does that add as much to the gender difference as when I have no ranking and add rivalry? Then they would be complements, or does it add nothing because one of the two is enough to create a difference in the substitutes? So we do basic analysis and compare model 1 with substitutes. And okay. Now, you can do, if you're comparing the rivalry together with private ranking, you can do two things. You can first have private ranking and see what happens when you add rivalry, or you can first have private ranking. Okay, so that's these two columns over here. What does this number say? If I add private ranking to rivalry, then the model of them being complements is more likely than, is almost 2.5 times as likely as them being substitutes. So for that case, it seems that adding rivalry adds something to the gender difference compared to having only private ranking. Adding private ranking to rivalry is more or less, both models are more or less equally likely. So for the private ranking case, if anything, they're sooner to be complements than substitutes. With a social ranking, that's completely different. Either adding rivalry to the social ranking or adding social ranking to the rivalry. In both cases, the model of substitutes is more than 50 times as likely to be correct than the model of complements. Right? So this means that we can conclude at least that social ranking and rivalry for resources are substitutes, and that the question of private ranking and rivalry remains unclear. Okay. So having social ranking and then adding rivalry doesn't do much. But it also works the other way around. So let's say you have social ranking and rivalry. And I would argue that in many cases of competition in the world outside the laboratory, you have both. And now let's say you're worried about the gender differences and you do some policy to take care of the rivalry. So you make it less competitive, right? What this means that the substitute means that that policy will not work if you still have the social ranking, right? A policy aimed at taking one of these two away is not going to work because the other one is still there and they are substitutes. Okay, so what mechanisms might underlie these differences that both social status and rivalry create, sorry. So our first result is we find that social ranking and rivalry are substitutes. Now we're going to look at possible mechanisms. First, maybe they just react differently in effort. That's for many reasons that's possible, simply because they might expect different retribution, or they might have different expectations about how to make them look, right? So maybe women just have lower effort than men. Well, if that's the case, these patterns that we already saw for performance would have to be the same as the patterns in effort, but they're not at all. In fact, in some ways they're opposite, because this is the only insignificant difference we found when we're looking at performance, and these are all significant. With effort, this is actually the only significant difference. Men make significantly more effort when there's no kind of competition at all. And all these other are not, and in some cases, women even make more effort than men. So we conclude that the differential effort response is not the underlying mechanism. A second mechanism, altruism. This is a new study. So here the idea is that when you are ranked, for example, you having a higher rank means someone else is having a lower rank. Right? And you winning a competition means someone else is not winning the competition. Now, it might be the case that men and women think differently about the effect that their rank or their competitive success has on others, so that altruism plays a role. Now, to study this, we focus on a private ranking treatment because that's the easiest way to create something where we can have, where we can take away the possibility of affecting others. And what we do is we take 5 participants from a previous sessions. We call this private historic ranking. In this way, your rank affects no one. The only thing is you hear about your rank. You hear how good you are compared to 5 peers. But the fact that you score well does not mean that anyone else scores worse, because that's all history. So if there's no altruism here, because there's no altruism, sorry, because altruism cannot play a role here, we expect no differences. So our hypothesis is that men and women will perform equally well. And again, because we're hypothesizing no effect, we have to do Bayesian analysis.
You have 5 minutes, including the questions.
Yeah, I should make that. So what do we find? No ranking and private ranking is what we already saw. Our hypothesis is it's going to be more like this in the historic ranking, and this is what we find. So to do the Bayesian analysis, we have one model that says private historic ranking is like no ranking, and another model says that it's like private ranking, and the odds ratio turns out to be 43-1 in favor of model 1. So it's much more likely that these data are generated by a model that explains this, than that these data are generated by a model that explains this. And so we conclude, when altruism can play no role, gender differences are unaffected, and therefore altruism may be, differences in altruism between men and women may be the underlying, or one of the underlying mechanisms. Third mechanism is about beliefs. So people just men and women might think differently about how men and women perform. So we elicit beliefs, but we do so conditionally on competitive conditions, because I might think that men and women perform equally when there's no competition, but I also might think that men perform better when there's rivalry for resources. So we measure beliefs for three key conditions: no competitive dimension, which is the benchmark, a rivalry for resources case, and the social status ranking case. To start, participants do the task. Then there's 3 more parts, 1 for each of those 3 competitive environments, and we randomize the order, and only 1 is paid. And then for each of those, you just have to predict, have men scored better at this, or have women scored better at this in the past? And they get 5 years if the selected part was predicted correctly. And if we look at the fraction of people that think women are better, so when there's no ranking, women and men both think that that about 40% of 40% of the women and 40% of the men think that women are better, but that's not significantly different than 50%. This is by a binomial test. When there's status ranking, for women, it's still not different than 50%, but men think that men are better. And in the same time, men think that men are better when there's rivalry. Right? This is the significance of the binomial test. Right? So men think that when there's some kind of competition, men are better. And that might be a self-fulfilling prophecy, right? Which means beliefs may be the underlying mechanism. Now, I'm going to skip this. We checked whether it makes a difference whether the same gender instead of mixed gender treatments. It turns out it's not, doesn't make a difference. So homophilia does not explain the effects. And then finally, you can ask, do women underperform or do men overperform with competition? We pooled the data for our non-competitive treatments and for our competitive treatments. And what do we find? Well, men perform better in competitive treatments. In non-competitive treatments, comparing men to women, women perform less. Sorry, there's no significant difference. There's no significant difference. So when there's no competition, even when we pool everything, there's no significant difference. In competitive treatments, men perform better than women, but also men perform marginally significantly better with competition than without, and women perform strongly significantly worse under competition than they do without competition. And I'll just leave these conclusions up here for you to read.
Okay, many thanks. So there's time for questions. So there were two in the chat in between, but my understanding is that they have been answered by Jordi already. Are there other questions? Anyone? Yes, Lenka, so I'll unmute you that you can ask. You say that, okay. Should be able to talk now?
Thanks, yes, it works. Arthur, thanks for the lovely presentation. I have one question. So I'm thinking related to your private and social ranking. I was trying to relate it to concerns about how I or my group are perceived by others. So I'm thinking of three types of social concerns that I might have. So I might be concerned about how I see myself. So I am not good at this task. I might be concerned about how others see me as a person. So Lenka is not good at this task. And I also might be concerned how others see my group. So women are not good at this task. Can your experiment to speak to these three concerns or only to some of them, and which ones?
Well, that third information is not given, right? So people cannot infer in our experiment whether women or men were better at the task. And so I'm not really, unless it works through some kind of stereotype beliefs, right? So that, let's say the C player is the only one who could, right? So let's say the C player sees 4 women and 2 men, and the 2 men perform better than the woman. Then if she already has stereotype beliefs, or he, then perhaps it might have an effect. I don't think that's going to override any of the other stronger comparisons that we have.
Okay, clear enough, thanks.
Okay, then thank you. And then I will take over. I hope you can see my screen. Maybe Venbo, you can overtake my role and stop me if I take too much time. This is okay? Cool. Okay, then I'll start right away. So thank you for being here. And I'm going to present this paper entitled Pushing Through or Slacking Off, which is joint work with Felix Schmidt from Deutsche Bank and Patrick Schneider, who's at the University of Würzburg. So I think this fits very nicely into the session, and so the motivation can be rather short. So the motivation is that many facets of life display something which we could describe as rank feedback or generally as relative performance feedback. We even have seen examples in this session already, for example, in settings where we have dynamic contests, but even more general ones. Of course, for us as economists, what matters or what we care about is how does receiving a certain form of rank feedback, so information about my relative performance, affect my subsequent behavior, particularly my effort choices, and thereby typically also my output. And when we think about it, and again, we have seen examples for this in this session already, then many potential mechanisms or many potential effects are conceivable. For example, we could imagine that people who get a very good rank feedback, that they try even harder, they are highly motivated and even improve their efforts subsequently and their output. But we can also think that receiving a very good rank feedback leads you to slacking off, meaning that you say, okay, I achieved this already, so I can ease out now a bit. Similarly, things we could think of behavior at the bottom. When you are in the very last rank, you could think that you really want to push hard. There is some papers which show that something like last place aversion, but it's also seems very reasonable that people say, okay, given that I'm last anyway, you entirely give up. So these very loose examples already show us that many things we can think of. And also when we look into the theoretical or the empirical literature, then we see that the effects of receiving rank feedback are all over the place. And so what we want to do with this paper is we don't want to say that this is not a right approach, but we want to rather take a different perspective on understanding what are the behavioral effects of receiving rank feedback. Namely, we want to ask that maybe given that there are so many potential mechanisms that we couldn't think of, is it maybe a fruitful and beneficial perspective to ask, is it the case that people are substantially and systematically different in how they react to rank feedback? So in simpler terms, is there something like a rank feedback type? So is it just that some people react in one way to rank feedback and other people react in another way? And so this is what we're trying to do in this paper. We want to try to put some structure on this heterogeneity that we conjecture. And this is what we do in this laboratory experiment. So before I explain to you how the experiment goes in detail, let me add some further points of motivation of why this matters. So first, again, keep in mind, so the goal is we try to identify something like rank sensitivity as an individual trait. So this links to other aspects of the literature where behavioral experiments have been used to classify individuals. For example, when we think about social preferences, where we know that there are many papers who show that classifications in order to, according to conditional cooperators versus free riders, or also with other preference domains like risk and time preferences, or which has also been discussed, competitiveness. So many of those papers show that you can use classifications based on experiments of individuals, embed them into other data sets and see how these measured preferences somehow explain heterogeneity in other settings. And so this is a bit the idea that we can take here, just using this approach for another dimension, namely for rank sensitivity. Why would this matter other than from this, let's say, foundational research perspective? Well, it might potentially help in organizing this apparently inconsistent empirical evidence. Because if we think about it, if there are very different types with respect to rank feedback, then depending on the distribution of types, the very same policy that you introduce, the same kind of feedback technology you implement in a setting can have very different aggregated effects depending on the underlying distribution of feedback sensitivity types. And also when we think about this from an applied policy perspective, then it means that if we find that there is this substantial heterogeneity in how different types react to rank feedback, then depending on how this characteristic is correlated with other aspects, for example, visibility and the like, imply very substantially different and non-trivial allocative and distributional implications. So think, for example, about tracking in school, when you have it that very high ability people are very rank sensitive, and in a particular way, then this might, depending on this correlation, increase or decrease inequality along different dimensions. So this is why we argue that this is a fruitful perspective to consider to what extent exists something like rank sensitivity as an individual specific trait. So how do we do that? Well, we run a laboratory experiment including two parts. So in the first part, we aim at, as precisely as possible, measuring an individual's rank sensitivity type. So we assess this heterogeneity in the reaction to rank feedback. And then in the second part, and this is important, of course, we see how well is our classification from the first part able to explain heterogeneous reactions to rank out of sample and also out of task, so using another task. Yeah, so the second part is, of course, a crucial element in seeing whether this classification of behavior within the first part is just an arbitrary structuralization of the data, or whether this is really getting to something which has at least some individual stability. Yeah. So how we do that, in part one, we let people participate in a series of dynamic contests in which, of course, they get intermediate feedback. Therefore, each individual, we look how do they react to rank feedback. This gives us an individual specific parameter of rank sensitivity. Then we expose the same subjects into another round of dynamic contests and see whether their reaction to the feedback in that contest is in line with the classification we had done from the first part. So we have this clear out of sample test, which is what is actually the key test of our idea. So the first round features the slider task. So I guess here I do not need to explain it just very shortly. Your task is to move as many sliders as possible using your mouse into the middle of the slider, namely to 50. So this is a very commonly used real effort task. And as I said, what we do is we put people in a series of dynamic contests. So what's the idea here? Well, recall that the goal of this first part of the experiment is to measure feedback sensitivity on the individual level. So to do this in a reasonable way, of course, this requires sufficient within subject data. So what we do is we put people, so every individual, in a series of 5 contests with 4 rounds each, which gives us 20 observations per individual. So based on these reactions of performance to the rank that they've received, we can estimate for each individual a feedback sensitivity type. So after each round, after each contest, we rematch subjects so that we have some variation there. Importantly also, we keep monetary payments orthogonal to the rank feedback. Namely, we just pay a flat piece rate out. The idea of this is just that we want to focus on these, let's say, psychological effects of receiving rank feedback, and we don't want to intermix them with potential tournament incentives on the monetary domain. Of course, they are very interesting, and we've seen in the session also already tasks with respect to that. Here, the decision to do that just follows the idea that we want to reduce the complexity and just focus on the, let's say, psychological motivational effects, which are not materially driven. Yes, and of course, such that people can react to feedback, we have to give them feedback. So over every round in the contest, you get feedback on your and your contestants' points and the rank that follow from that. So of course, when we think about how do we estimate this, a very obvious identification problem arises, namely when we want to regress performance in one round on the rank you had from the previous round, then of course an endogeneity problem exists, because variables like ability should drive both of these factors such that we would get biased results. So in order to identify the individual reaction to rank, we need some source of exogenous variation of rank. How do we do that? Well, we implement in the very first round of each contest an individual specific multiplier, which multiplies the performance you have in this round and increases the points you get from your performance. Importantly, so subjects are aware of this multiplier technology. However, what they are not aware when they enter the first round is which of those different multipliers they actually get. This means that in expectations, the productivity of the effort is constant. However, after the first round, the multiplier is realized and gives an exogenous source of variation in their rank. So given this data, what can we do? Well, we can do a 2SLS estimation in which so we estimate so we regress performance in one round on rank after the previous round, and we instrument rank after the previous round using the realizations of these different multipliers as an instrument. So before we actually go into the individual level, let me first, as a benchmark, show you the results that would come up if we would not look at the individual estimations, but rather would estimate this on the aggregate and just look at average treatment effects. So this is a table which would get out of this. And then what we see is we see a positive effect of rank on subsequent performance. Importantly, rank is here defined such that a higher value is a better rank. So the interpretation here is quite clear. We see that on average, people react positive to a better rank, meaning that if they get a better rank, they perform better afterwards. And if they get a worse rank, they perform worse afterwards. So far, this is nothing particularly new. Studies like this have been done. And we would conclude now here, okay, so giving people who are good rank feedback is actually something which improves performance. Giving people who are bad rank feedback decreases their performance. However, of course, the key idea is to now look at these feedback sensitivities at the individual level. So how do we do that? We apply the same empirical strategy than before. However, the difference is now that we do this regression for each individual separately, which gives rise to one individual feedback sensitivity parameter beta I for each individual. What we then can do is we can classify individuals according to these estimated beta I's. And what we do, and to put some interpretation to it, we call people who have a positive beta amplifiers. What's the idea? Well, people who have a positive beta, they increase their output when they are at the top, and they decrease their output when they are at the bottom. Hence, they amplify initial differences. While people who have a negative beta, they react entirely opposite, which means that they dampen initial differences. And people who have a beta close to 0 are non-sensitive. they do not have a systematic reaction to rank. So if we do that and plot it now, so these individual specific betas, then we see that, of course, our aggregate perspective was not wrong in this sense, because we see on average, it's the case that people are amplifiers. However, if we just would conclude from our aggregated results, people react like that, we would see that a huge part of our subjects actually don't react at all. So the people, the gray people in the middle. And even more importantly, a huge part of our subjects even behave entirely opposite. So meaning that the estimated effect of rank feedback for this lower part here, the red shaded participants, they would react entirely opposite to what we would have concluded from the aggregate perspective. So intermediate summary from our first result, our conjecture that there is a huge heterogeneity in how people react to rank is actually valid. Now, of course, comes the important part. We want to see, is this classification something that has some robustness? So can it actually hold out of sample? Or is this just very random? And if we would run this again, the same people would be in a very different classification. So to do that, we now put them to another contest. To make this test even harder, we also use a different task. So instead of the slider task, now we use an adding numbers task. So we make this test a bit harder, because this means that for our result to hold, it means that people have to have the same type across different tasks. Of course, also here you might know that, or it's very simple to see. The task is to add as many numbers up in a given time as you can. So what else is different? Just let me highlight the differences in the second part of the contest to the first part. Well, first, I already said we have a different task, which is adding numbers. Second, we also, and this makes the test again a bit harder, we choose a different source of exogenous variation to identify these individual rank reactions. Namely, we start out with fixed rounds in which people perform, carry out the task, but don't receive rank feedback. But rather what they get is they get just their fixed piece rate. And these 6 rounds we use later as a measure of individual ability. So what we then use as a source of exogenous variation to identify rank effects is we look at the random assignment of your contestants and use their average ability as an instrument which affects your rank and fulfills the exclusion restriction. Further difference, we now have 6 contests where we have only 2 rounds each. So then again, our strategy is basically the same. You see, the only difference is here in the first stage, we have a different instrument. We use the minimum of the ability of your 2 contestants and use this as an instrument. Now recall what we want to do here is we do not want to classify people again, but we rather want to check whether our classification from the first part of the experiment works in the second part. So how do we do that? What we do is, in order to increase power of our test, we summarize our heterogeneous, so our predicted heterogeneous treatment effects into this one coefficient. So we have here this interaction term SI, which is exactly following from the classification which we had in the first part. And we see that how to define it is that SI is 1 if individual I was classified as an amplifier, and -1 if it was classified as a damper. So what gives us, the specification gives us the following idea, that all the 4 different predictions of heterogeneous behavior all lead to a beta which is positive. So recall, what are our predictions from the first part? Well, people who are amplifiers, they should react positive to receiving a first rank, while dampers should react positive to receiving a last rank. Amplifiers should react negative to receiving a last rank, and dampers should react negative to receiving a first rank. So as you can see, all these 4 predictions are summarized in this interaction term, because all these 4 predictions in isolation predict a positive value of beta. Hence, if we now look at this beta coefficient, if it is positive, this is a joint test of our 4 heterogeneity predictions.
We have 5 minutes left.
Sorry? Yes, okay. So what do we see? So you see here the interaction term is exactly as we hoped for, or as we predicted. So we see this positive beta, which means that the heterogeneity, so these are all standardized coefficients, by the way. So we see that people who are classified as sensitive indeed have a significant reaction in the direction in which we predicted according to our classification from round 1. So again, consider that these are entirely opposite effects. People who have been classified as amplifiers, they react as an amplifier, while people who were classified as a damper react as a damper. In the second column, however, you see that people who were classified as non-sensitive also do not show a systematic reaction to rank feedback. Yeah. So what we conclude from these results is that we see that our classification from part 1, so seeing how do people react to rank, and using this classification to predict their behavior out of sample, out of task, and also using a different source of exogenous variation, we see that our classification works in correctly predicting how people react. Important point, so I explained how this test summarizes all our 4 predictions into one parameter. If we look at this in isolation, then we see that none of the 4 predictions is contradicted by splitting the sample up. So when we look only at amplifiers and dampers as first or last point, we all see that all these coefficients are positive, so that for all 4 sub-tests, so to speak, we go into the right direction. So some additional findings before I close. So what I don't have in detail here, we also dig a bit deeper into the mechanisms that are there. And what we see is that the effects are particularly strong if the competitions are tight. This, in our case, in our view, is an indication that people use rank information in instrumental information sense, meaning that they really have an intrinsic value for getting a better rank or something like this. And it's not something like a simple momentum effect of having a motivational effect of just receiving good feedback, but unfortunately not enough time to get into detail here. And the second interesting thing is that we see that our rank sensitivity is actually not correlated with any standard characteristics we listed in the lab, so neither with age or gender, field of study, also not the big 5. And in earlier versions of this, we also checked for competitiveness, and there was also no correlation. So this is just the result, whether it's nice or bad, depends on your evaluation. I think it's interesting to report. So let me wrap up. So what we find is that we have substantial heterogeneity in how individuals react to rank feedback. And more importantly, even we see that such a classification is able to predict heterogeneous treatment effects out of sample and out of task. So this gives rise to this idea of rank sensitivity of being potentially an individual specific trait. Implications are that when we introduce feedback policies, depending on the underlying distribution of feedback sensitivity types, the effects might be very different, also with respect to distribution. And secondly, this means that when we want to extrapolate the effects of feedback, then this might be a problem for external validity. Some 2 outlook things that we think as next interesting steps. First, develop an easy to use measure for rank and feedback sensitivity. So something which is much shorter, survey-based or behavioral-based, let's see. And second, we want to try to what extent our approach is able to better explain, so better predict the data that is out there from existing field studies, from existing observational data, where we have people that receive rank. Okay, yes, thank you. So I have to stop, yes. Okay, I don't know if you have more time. We're probably almost up. Menbo,
we have time for questions. This channel won't be used for an hour.
Okay, cool, okay. So, okay, I just open Avi here.
Thank you very much. A very, very interesting presentation, very interesting paper. Actually, I'm not going to ask you a question. I'm just going to say that I think this might have some very significant implications. And I'm thinking about the education system. I'm thinking about elementary school kids. I'm thinking about high school kids. I'm thinking about people having very, very different types of reactions to what's going on in the classroom, and how getting this type of experiment, if you can actually, really figure this out and figure out, how you would test children to find out what types they are. When you're dividing classes, when you're dividing different types of things within the classroom to be done, you can motivate different children in different ways. And that's super important for so many things. So well done.
Thank you. Yeah, I fully agree with that's what we're thinking about next. So I'm happy that you bring it up. So, Lisa, so Philip, is it okay that we keep going? Because I think I don't want to overtake the time. Yeah. Okay, so Lisa, I unmuted you. Hi, Lisa. But I can't hear you.
Lisa, we're not hearing you. No, you're not muted, but we're not hearing you.
Yeah.
So does it now work? Do you hear me?
Now it works. Yes, yes.
Okay, thank you. Sorry. Thanks for the interesting talk, Florian. I have one question regarding your classification into types. So you told us that you classified the subjects into amplifiers and dampers. And by this, in a way, you assumed that people in a positive and in a negative position in the ranking react in the same way. So what makes you confident that it's okay to do this summary in a sense?
Yeah, that's a very good point again. So not just saying that, so this is something which we have spent some time on. So we have done some tests which all actually confirm that this classification is okay. However, we're still in the process of thinking how strong are those tests. So our heads go back and forth. So what parts of these tests are just simply mechanical results of our design? So this is exactly what we're currently looking at. So the only thing I can say at this point is that all the tests we have run, they are confirming this assumption, which is a strong one, because initially we thought it could have different types. And secondly, of course, what adds to this is that if this assumption would be strongly violated, then we should have problems finding the effects in the second part of the experiment. But still, it might be more complex, how people react to it. This amplifier versus damper classification, how much of a restriction it is not so clear to us yet. Yeah.
Thank you.
Okay. I would of course love to, but I don't want to extend the time anymore. So I thank all the speakers, all the audience for a great session. Thank you all. And have a good time in the remaining conference and hope to see you around also soon in person again at some point. Thank you, Philip, for the technical support. I think we close it here.